My name is Nika Durham from the National Renewable Energy Laboratory, and I'd like to welcome you to today's webinar on the first of its kind study, demonstration of essential reliability services by a 300 megawatt solar photovoltaic power plant. I'm here with the project team from the National Renewable Energy Lab, or NREL, California ISO, and First Solar. During today's webinar, the team will detail key findings and results from the study and what this means for the energy industry. We'll give folks a few more minutes to call in and log on. So while we wait, I will go over some logistics and then we'll get going with today's webinar. I want to mention that this webinar will be recorded and everyone today is on listen-only mode. You have two options for how you can hear today's webinar. In the upper right corner of your screen, there is a red arrow. If you click on it, it opens the webinar toolbox, and there is a tab that says Audio. This will allow you to choose whether or not you want to listen to the webinar through your computer speakers or a telephone. We will have a question and answer session at the end of the presentation. You can participate by submitting your questions electronically during the webinar. Please do this by going through the questions pane in the box showing on your screen. This is accessible by clicking the red arrow again, and the questions box is in the list. You can open it to type in your questions that you have during the course of the webinar. Our speakers will address as many questions as time allows after the presentation. Before we get started with today's webinar, I'd like to introduce you to our panelists. With us, we have Vahan Gevorgian, Chief Engineer at NREL, Clyde Loutan, Principal Advisor of Renewable Energy Integration with California ISO, and Mahesh Morjaria, Vice President of PV Systems Development at First Solar. The purpose of this webinar is to share results of pioneering work conducted by CAISO, First Solar, and NREL that was aimed to breaking new barriers to the provision of ancillary services by PV generation in terms of both plant capacity and system-level impacts. The team is excited to share the results that the project demonstrated through real-world testing that PV power plants can contribute to maintaining grid reliability. Now let's go ahead and get started with the webinar. I will first pass things on to Clyde.
Well, thank you, Nika. Can you guys hear me okay?
Yep, we can hear you.
Okay, so before we get started, first I'd like to give a real brief background as to why we decided to do this comprehensive test. Most of you may already know that California has very aggressive energy and environmental policies, and these policies are driving, renewables integration, and of course, we started to see the grid transforming into something new today. I'd also like to talk about some of the operational challenges we're seeing currently, talk a little about what are the essential reliability services to integrate higher and higher levels of renewables into the grid. How does the ISO plan on meeting these operational challenges? And then I'll pass this on to Mahesh after so that he can talk about the 300 megawatt solar plant that we tested. He would talk about the configuration, the capabilities of that plant. And then we pass it on to Vahan to talk about the tests that we conducted and the results of those tests. So with that, I'll move on to the first slide. First slide here. Okay, so real quick about California ISO. We have roughly about 71,740 megawatts of power plant capacity. It's a fairly large system. We peaked back in 2006 at 50,270 megawatts. We currently serve 80% of the load in California, and it equates to about 30 million people. What I really wanted to focus on here is the 71,000 megawatts of capacity. Of that, roughly 20,000 megawatts is renewables. And of that 20,000 megawatts, we're looking at roughly half being solar. So currently, what we have is about a little over 10,000 megawatts of transmission-connected solar. We got roughly about 5,500 megawatts of rooftop PV. We have close to about 5,800 megawatts of wind on the grid. The rooftop PV currently does not count towards RPS. So we get into that a little more. So with the energy and environmental policies that's driving, the need for the renewables, is one of the things, we got to do by 2020. We got to reduce the greenhouse gas emissions back to the levels we saw in 1990. By 2020, 33% of the load that's served in or within the California jurisdiction or in California as a whole, that needs to be 33%. And then this bottom one-through cooling power plant capacity, this is roughly about 12,000 megawatts of capacity that we have on the coast. It uses, or these plants uses the sea to cool the plants. What happens is the water goes back out a few degrees higher than it comes in. It's causing problems to aquatic life. And most of those plants will either be retired or retrofitted. So there's some uncertainty surrounding the one-through cooling plants. Also, the loads. We have a lot of things are happening currently with loads. In the past, loads was pretty much temperature dependent. You can predict loads pretty well. Today, with energy efficiency, the rooftop PV, electric vehicles, price responsive loads is getting a little more and more difficult to predict. So with unpredictable demand and variable supply, it's causing some challenges for us. And hence one of the reasons why we decided to do this test. Also, we're looking at over 1,300 megawatts of electric storage that's supposed to come in by the 2020, 2024 timeframe. And it's expected, or we expect to see about 1.5 million to 2 million electric vehicles on the road by 2025. The current governor has some plans for 2030. The current demand is, by 2030, 50% of the load served in California needs to be from renewables. He also would like to see a 50% reduction in petroleum, 12,000 megawatts of rooftop PV, and as I mentioned, rooftop PV does not count towards renewables, but it impacts system frequency. We see there's some challenges there. He wants the energy efficiency from existing buildings to increase, and then of course greenhouse gas reduction to 40% below the 1990 level by 2030. So that's pretty aggressive. So with that, this is our current expected behind the meter installation. So by the end of 2016, we saw about 5,400 to 5,500 megawatts. And currently for 2017, the expected growth is about 134 megawatts a month. And we anticipate hitting about 12,000 by 2020. So what we show here is at the end of 2016, we have close to 20,000 megawatts of renewables on the grid. 4,000 megawatts of that is about the geothermal, biomass, biogas, run-of-river hydro. And then we got roughly, by 2020, we expect another 3,000 to 4,000 megawatts of, we think mostly it's going to be solar PV to meet this 33%. And then between 2020 and 2030, we expect an additional 10 to 15,000 megawatts of renewables to make that 50% by the 2030 timeframe. Most of you may have seen this plot here. We created this about 4 years ago to show as more and more solar comes onto the grid, some of the challenges we'd expect to see. This plot really shows you here, during the middle of the day, we expect to see oversupply situations. Then towards the evening, we expect to see a huge ramp Back in 2012 timeframe, we had anticipated a 13,000 megawatt ramp by 2020. While last December, we already saw pretty close to 13,000 megawatts. And then last weekend, we saw the net load, which is the load minus wind minus solar, drop to below 10,000. It was 9,187 megawatts. So when we initially did this plot, we completely underestimated the rate at which rooftop PV was going to come onto the system. So this dark that we created is real, and it really tells the point of oversupply. Today, we tend to see a lot of negative prices, from about 10, 11 o'clock to about 3 o'clock on evenings. And the other thing we did about 4 years ago, we wanted to show the need for flexible capacity on the system. So the second slide, I didn't get a lot of time to talk about that, but that shows you today what we started to experience. So when you stack your non-dispatchable generation, you look at what comes in on the interchange, and then you look at wind and solar. So this is the top right curve. You see that red area there. This is where we start curtailing resources on the system because you have too much generation. The system frequency tends to go high, prices go negative, and there's nothing else you can do but curtail. So with that, most of you that operate the grid familiar with controllable devices. Okay, so on your controllable resources, your daily profile will look more or less flat or controllable. Now, when you look at solar production, and this is looking at the first 2 days of the first week back in 2014, and it's similar to what we see today. You can see how different it could be from one day to the next. If you look at consecutive days, so we look at the whole week as to what the solar production was. This causes some challenges for the forecasters. And again, when the operator operates the grid, he needs to maintain 60 cycles. You need to make sure you have enough flexible capacity, enough regulation on the system to meet all of this variability. Typically, when we plan the system, we plan based on averages, and that red curve really shows you the average for that week. But on the operator side, we need to deal with all of these variability. Now, in the old days, we had just load, which was variable. Now, when you look at part of your supply, which is solar here, it varies quite a bit. And then when you look at your wind for this same week, the wind almost looks similar to your solar profiles. So for this same week, when you look at the wind profiles, you can see how wind varies from one day to the next. So the challenges we have in the day-ahead time frame now is trying to predict what the wind's going to be doing, what the solar is going to be doing, what the load's going to be doing, what the rooftop PV is going to look like. And then again, when you look at averages, it looks pretty flat. But this is really challenging. You see a lot of variability from 1 hour to the next. Even within the operating hour, you see a lot of variability. And this drives the need for things like flexibility. It drives the need for other types of controllable devices on the system. So with the wind and solar profiles, what we started doing here at the California ISO, and I'm waiting for the slides to advance here. Okay, we started looking at the control performance. So in the US, we have something we call Control Performance Standard 1, which is just a statistical measure of your control area errors. You combine that with the interconnection frequency deviation from schedule, and it really comes down to each balancing authority within an interconnection has a responsibility to help control the interconnection frequency. So what we started doing, before I get into that, this is something that we report to NERC on a monthly basis, and it's average across 12-month rolling average. But what we started doing here at the ISO is looking at hourly. Each hour, we wanted to see how well we control the interconnection frequency, or if we tend to lean in certain hours. So if you look at the blue bars is really when it's above that green line. That green line is 100%. So everything that you see that shows up blue within the hour, it means that you help support the interconnection frequency. When you look at the red, you tend to see, well, we had some challenges during those hours. So this plot shows you the control performance for that hour. It also shows you the net load, which is that red curve. And well, we started looking a little closer. Well, why did we have challenges in those hours? When you start overlaying things like your wind, your solar production, you started to see some very interesting results. So this is actual data that we saw back last year. And this was a windy day. So when you have a windy day and you look at the yellow is your solar production, green is your wind production. And when you have variability like within the operating hour, so in 1 hour and half an hour, you lost 1,300 megawatts. In the second half an hour, you increase by about 2,300 megawatts, then you drop off by about 1,500 megawatts. If you forecast is not dead on, very close to accurate, then these are things that you don't see in real time. These are the things you need to make sure you have enough regulating capacity or flexibility within your operating fleet so that you can make sure you could meet some of the variabilities and intra-hour uncertainty that we started to see. So when you have a lot of wind and solar on the grid, especially when it's a cloudy day or a windy day, this is what the production would look like. And we got to figure out ahead of time how you're going to deal with things like this. We think the control performance standard tells us a lot as to what it is we need on the system. Using this information, what we did is we did some more evaluation on the grid. Before these slides advance, I'll go over some of those. So during the course of the past few years, we started to see the increased need for regulation. So we balance the system here on 2 time frames in real time. One, every 5 minutes, we balance the grid based on economics. So we forecast what the system is going to be next 5 minutes, and then we dispatch the most economic units in state and what we can get on the ties to meet that load demand. So, and then every 4 seconds, we dispatch regulation to meet the intra 5 minute variability on the system. What we started to notice also is the ramp. So that even ramp, as I said, it's already 15,000 megawatts. We anticipate that to be closer to 18,000 megawatts by 2018, 2019 timeframe. Within the operating hour, now with the variability and uncertainty, we need to make sure we have sometimes between 4,000 to 6,000 megawatts of capacity so that the market would have resources to dispatch, because the system can change quite a bit. Being able to forecast that change ahead of time sometimes could be challenging. We also see during the middle of the day that oversupply situation that we talked about, where the prices go negative, frequency tends to go high. What makes it a little more challenging for us is in our system, we got a diverse resource mix. So when you look at things like geothermal, biomass, biogas, run-of-the-river hydro, we have to about 8,000 megawatts, and on some days could be as high as 10,000 megawatts of non-dispatchable generation. So on the second slide, when I showed the net load dropping to below 10,000 megawatts, you can see some of the challenges that we started to see, because now you do not have a lot of headroom to commit units to meet things like frequency response, to make sure you have enough capability on the system to meet all the real-time control performance standards we have to meet. And then the other variable on the grid is the rooftop PV. We're still trying to figure out, and I think the industry as a whole still trying to figure out what the impact rooftop PV has on the transmission operation. So with 5,000 megawatts of rooftop PV, this year the California ISO is embarking on a study trying to figure out what impact that has on real-time operation. And then the last slide before I pass this on to Vahan, I would show some of the things we're planning on doing here at the ISO. One is the conventional generation is what we need to help. We're also looking at storage, and I mentioned that by 2020-24 timeframe, the mandate in California is 1,325 megawatts of storage by that time frame. We also look at demand response, loads. Loads should play a huge part in integrating higher and higher levels of renewables. But last but not least, we think as more and more renewables come into the system, you need things like frequency control, voltage control, ramping capability, and we believe that renewables themselves can help integrate or balance the grid to integrate higher and higher levels of renewables. So this was one of the big drivers for us embarking on this test. We wanted to see the advanced inverters, the controllability to control these devices, how well they can provide, one of these inverter-based resource could provide the essential reliability services that we need to maintain reliability. Now, with that, I'd like to pass this back on to Nika, and then Vahan can take over and talk a little about the plant itself and the capability.
Okay, thank you, Clyde. We're actually moving on to Mahesh, who will be leading the next several slides. And it looks like, Mahesh, are you all ready to go?
Yes, I am. Thank you. Hi, this is Mahesh Morjaria from First Solar. What I'm going to do over the next several minutes is describe to you more about the project itself, and particularly the PV plant and how we control it in order to meet this particular goal, which was to demonstrate the ability of utility scale PV power plants to provide important ancillary services to the grid. More specifically, we wanted to actually look at the real field data and demonstrate the performance of that using that, as well as support CAISO in this case to adopt to these new operational practices and market mechanism to integrate higher penetration of renewables. Now, the project itself, the three parties, this is CAISO, NREL, and First Solar got together on this particular project. And we selected a site which is a 300 megawatt PV power plant, which was just established in California, and it's feeding into the CAISO territory. We conducted the testing in August 2016, and CAISO subsequently released a public report, which has been published as well. So let me start, first of all, describing the power plant itself. This power plant was built by First Solar. If you guys are not familiar with First Solar, we are a large PV module manufacturer. We have probably about more than 17 gigawatts of PV modules globally. And more specifically, we have about more than 6 gigawatts utility scale PV plants experience, and I've been building utility scale PV plants for the last 6 or 7 years. And in this particular plant, it was about 300 megawatts and utilized 4 MVA PV inverters. These are some of the largest inverters that we have developed with GE and utilizes a 1500 volt DC architecture. So besides the picture that you see on the top right, the bottom one is an illustration of what the plant architecture looks like. And here, for example, we're showing the PV inverter, in this case, the 4 MVA. Each of these block, which is designed, was about 40 MVA block. So that consists of essentially 10 inverters in that block, and we had total of 8 blocks altogether. And the collection system, which is very typical in utility scale plants, is a 34.5 kV collection system. And finally, all that power is aggregated and feeds into 2 transformers. They are 170 megawatts each. And they, in turn, the power is aggregated on a common bus, and it feeds into a 230 kV transmission line. So that gives you a rough idea of the overall plant. And by the way, I should also mention that we have two phasor measurement units, PMUs, on both of these lines, so that we can actually get a very high resolution data about the power and the phase angles, etc., to be able to make adjustments as necessary. Now, let me talk about the plant control system, because that is a key enabler in providing this capability. This is something that we have been developing over the last several 5-6 years, and have implemented in most of our utility scale PV plants. So here in the illustration shows at one end are the PV module arrays, which basically convert sunlight into DC power. We use combiner boxes to aggregate the DC power, which then in turn feeds into the inverters, which converts the DC power into AC power. And then we step it up with transformers to a collection system voltage, do more aggregation of that power, and finally aggregate that to a substation where it is stepped up to transmission level voltage. So this is a pretty simplistic way of looking at PV plant. So in addition to that, we have a SCADA system, which allows us to provide the operational data, access to the operational data of the plant, and a power plant controller that we developed and is a patented development that we carried out, which basically is like an orchestra conductor. What it does is that it monitors the grid conditions. It measures the grid conditions, for example, the voltage or power output, etc., and then communicates to the inverters, which in many of the large plants would be several hundreds of these inverters, and it essentially coordinates their output or the conditions. And particularly, we send individual signals to the inverters as opposed to mass broadcast or something like that. This is because in general, each of the inverters sees different conditions based upon the irradiance and the DC collection system, etc. And in essence, this is a closed loop control system, so that we can use that system to control the output of the power plant. And this closed loop system performs at 100 millisecond loops, so that we can actually control the output of the plant in a much faster manner than is sometimes possible with other kind of generation. With that in mind, the way we carried out this test was from a remote center, which is located in Tempe, Arizona. This is the picture of the remote center. And from that, we can access this plant, which was in San Bernardino County in California. And from the remotely, we can supervise the testing activities. We had both the CalISO and NREL team there, and they would suggest to us, hey, how about performing this test versus that test? And we could carry out those tests, see the results, and collect the data as such. We tracked the plant performance using that approach. And where necessary, we made changes in the set points and control parameters as needed. So this pretty much covers what I had in mind in terms of describing the overall system, the control system, as well as the power plant that we use for performing this test. And now I'll pass it on to Vahan, who is going to talk more about the testing results themselves and take you guys from there. Thank you. Vahan?
Yes, thank you, Mahesh. Hello, everyone. My name is Vahan Gevorgian. I am with National Renewable Energy Lab. So I was representing NREL team in this project. So as previous speakers mentioned, the project team was focused on this pioneering demonstration concept. We also developed a test plan in a close collaboration between our teams and the plant owner to show how various types of active and reactive power controls can leverage PV generation's value from being a simple variable energy resource to a resource that provides a wide range of ancillary services. Another major purpose of this project is, with this holistic demonstration and dissemination plan, is to close some gaps that exist among various stakeholders in California, nationwide, and actually worldwide on the role of PV in the future power systems. So as Mahesh mentioned, there is a project report published. It's available on both California ISO and NREL website. It can be easily Googled and found there. So currently, only a few grid operators in the US are using renewables, especially curtailed renewables, as a resource. And it's mainly done for a wind generation. And with this work, we wanted to show that similar services can be provided by PV, whether is it in curtailed mode or non-curtailed mode as well. So before moving forward, just a quick step back. U.S. Department of Energy, in anticipation of its major changes in a future operation landscape, especially for power systems with a high level of PV penetration, in the previous couple of years funded 2 smaller scale demonstration projects, both at about 20 megawatt scale in Puerto Rico and West Texas. And in this slide, you see the project teams and the First Solar. We go back in First Solar in this for this preliminary project as well. So these are also very advanced projects that demonstrated advanced controls by PV generation, including new controls such as fast frequency response and so on. One remarkable aspect of this test, like in Puerto Rico, we had hours of operation when this 20 megawatt PV plant was the only resource in the whole island providing frequency regulation when conditions were right. So this was actually real demonstration, a real system with PV providing all these services. This is a summary of conducted tests on California, in California ISO on this 300 megawatt plant in 2016. So the tests roughly can be broken into main categories: tests that do various types of active power control of a plant, and tests that involve voltage or reactive power control. So you see number of tests listed here. For majority of the tests, we had to develop a customized test plan and actually adjust plant controls to be able to do it. For certain tests, we used more standardized commissioning test protocol that First Solar is using for their commercial plants and adapted them to produce more test results. And all the tests we conducted are listed here. So this is an example of one day of testing. There is a several hour of test data as measured by those PMU units at the plant high voltage terminals. So these are active and reactive power control series, time series. And the yellow one on the top is the actual voltage as it measured on 230 kilovolts. So as you can see, this is not a typical profile production profile that people expect from PV plant. Simply because we're conducting many tests during this particular day and consecutive days. There are many tests compressed in this time series, but the main takeaway from here, you can see that PV plant, large PV plant, can curtail very fast down to pretty much zero generation in about 10 minutes and come back as fast. It can respond very fast to different active power control signals. And in the second half of the day, you see that the only changing characteristic is reactive power. And when it is changing, it's of course impacting the voltage on a 230 kilovolt line. And again, there is number of tests compressed in that second half of the day. Another takeaway from here, when active power is swinging a lot, the reactive power is largely basically non-impacted, and vice versa. When we do these large swings in reactive power, is not impacting the active power. So it's one demonstration of independent control of active and reactive power by inverter coupled generation. So this particular test shows the curtailment control of this plant with a particular ramp rate. In this case, we utilize 30 megawatt per minute ramp rate capability. So the PV plant under test is capable of deploying all 300 megawatts of its spinning reserve in only 10 minutes. Well, assuming some hypothetical case of full curtailment, of course. Another important thing to notice from here is that the plant can provide non-spinning reserve as well, not just a spinning reserve. In fact, in a PV plant, unlike any conventional generation, there is no differentiation between spinning and non-spinning reserve capacity due to the nature of a PV generation as an inverter coupled resource. So you can see here that the plant follows the set point, active power set point, very accurately, and it's tracking very accurately its 10% of rated capacity per minute limit. Another type of test we conducted is a PV plant participation in the AGC. And of course, in order to be player in the AGC market or frequency regulation market, especially for up-regulation, the curtailment is required. So for this particular case, the power plant was initially set to operate at the power level that was 30 megawatt lower than the estimated available peak power. So the green line here, or green trace, represents the available power from a solar resource, and the orange one in the bottom is essentially curtailment limit. So on top of that, the actual AGC signal, well, I take it back for a second. The historic AGC signal that California ISO provided to a conventional power plant of a similar capacity was provided to power plant controller to evaluate how well it can follow the set point signal. The decision was made not to feed the actual AGC signal in there in order not to cause any disruption in existing market operation. So the red trace in there is the commanded AGC set point from a historical data, and yellow is the actual power measured at the plant terminals. So you see from here, the plant tracks that set point, is tracking it very well, and is also capable of maintaining that 30 megawatt headroom. And this test was conducted during several times of the day under different resource conditions, morning, midday, and evening. In this particular slide, we'll just play animation of one test for you guys. So this is the real data, but played probably 10 times faster. So this is an example of an AGC test during the afternoon ramp when the solar resource was actually varying. So you see certain periods of time when the cloud was moving over the PV plant and the available resource is declining and then coming back. And you see that even under such conditions, the plant is capable of maintaining that 30 megawatt headroom very well, and also following the scaled down AGC signal. So the XY graph on the bottom basically shows correlation between set point and measured active power for different times of the day. Each color represents different time of the day. You see it's very linear with very high level of correlation. Another time series on the bottom right is basically a error in expressed, or AGC control error expressed in the percentage of a plant rated capacity. So you see that the maximum error there is within plus minus 2%, with which roughly translates into plus minus 5 megawatts or so of power. This is something that can be corrected with a very small amount of energy storage, but what is most important, this can be corrected by geographical diversity. As many and many of PV plants participate in this type of service, the aggregate accuracy of a whole PV fleet will be much better in per unit because main component in this AGC error is a small amount of resource variability, which is a random in error, and it's anticipated to be smoothed out as larger plants participate in this. This is this table here show the regulation of accuracies of a measured PV plant compared to conventional generation that currently operates in California ISO for comparison. So by comparing the PV plant testing results on the upper table to the values of individual technologies shown in a lower table, one can make a conclusion that regulation accuracy by PV plant is 24 to 30 points better than fast gas turbine technologies. So the data from this test will be used by California ISO in the future ancillary service market designs to determine the resource-specific expected mileage toward regulation up and regulation down capacity, And again, trying to make very important point. Remember, this is just one PV plant. These accuracies will be much better if there is more and more PV resource participate in this, and with an accuracy actually getting close and close to 100% when you have more and more resources provided this service. The next type of test we did was to demonstrate the ability of a PV plant to participate in a primary frequency response. So the ability of power system to maintain its electrical frequency within a safe range is crucial for stability and reliability. And the frequency response is a measure of an interconnection's ability to stabilize the frequency immediately following the sudden loss of generation or load. The sudden loss of generation or load manifests itself in a large frequency excursion. Due to limited amount of a project time we had with this plant, we couldn't have a luxury to wait until this event happened naturally. So again, we just provided a historically measured frequency event data measured in a U.S. Western interconnection frequency time series to a plant controller, and we measured the plant's response, providing the plant ability to providing the frequency group under different set points. In particular, we tested 3 and 5% under and over frequency events. The plant was commanded to have about 20% headroom. We also implemented the droop deadband. We used conventional 36 millihertz deadband there, and with using the actual frequency event. So on the right upper graph, the white trace represents the frequency event, historical event measured in a west, which is roughly equivalent of losing about 800 megawatts of generation. And the yellow trace is the actual measured response of a 300 megawatt PV plant. So the same test is actually expressed in an XY graph on a bottom right, and you see that this is a really linear, almost textbook-like frequency response. And again, remember, this is the PMU data, a very fast data, but you see very little scatter, even under slight variability of a solar resource in this test, so that you can see a deadband and then linear response of a plant with under frequency event. So this is a summary of many tests we conducted under different resource variability conditions during different time of a day, with the different group settings. And this table is actually summarizes the mean error, some statistics of the control error when plant is providing the droop response. And this is all expressed in percentage. If you translate it in megawatts, you see that it's a very small error. So the accuracy of its response is really remarkable, and it's much better than many conventional technologies can ever provide. These are the similar tests conducted for over-frequency event. Again, the white trace on the top is the actual over-frequency event measured in a west that was played on a plant controller terminal. And the yellow one is a plant reducing its output in response to it. And also you see a couple of XY graphs in the bottom showing the linear correlation between frequency and power in this droop response. There are a number of other tests we conducted. This is an example of more standardized commissioning tests done by First Solar when a plant is responding to some step changes in frequency, and you see that calculated power response and actually measured power response are basically on top of each other. So that shows that plant also can provide fast frequency type of responses very efficiently. The other type of test we demonstrated here is a voltage regulation and reactive power control type of test. So voltage in many power systems, in bulk power system, is normally regulated by generator operators. And this type of services are typically provided with voltage schedules by which transmission operators set. So growing levels of penetration of variable wind and solar generation are leading to the need for them also to contribute to power system voltage and reactive power regulation, because in the past, the bulk system voltage regulation was provided almost exclusively by synchronous generators, and this landscape is changing fast in many places in the US. So conventional synchronous generators of power plants, they have reactive power capability that is typically described as a D curve, shown on the left of this slide. The reactive power capability of conventional power plants is limited by many factors, of course, including thermal limits, max and minimum load capability, and also stability limits. So, and the ability to provide reactive power at zero load is usually not possible for many large plant designs unless it's designed to operate as a synchronous condenser. Theoretically, reactive power capability of PV inverters is determined by its current limit only. So with proper megawatt and with the same megawatt MVA ratings, the PV inverter should be able to operate at full current with reactive power capability similar to one shown here in general, which is of course theoretical. So for the same MVA rating, a PV power plant is expected to have two-quadrant operation. So it's essentially this yellow area on this graph, and it's supposed to have much superior reactive power capability than a conventional synchronous generator-based plant. So that's what we try to demonstrate by this particular testing. In its proposed reactive power capability characteristic, which is shown in the right, for the California ISO actually proposed this reactive power capability for asynchronous generation. It defines the requirements for dynamic and continuous reactive power performance by variable resources, and we actually use this as a guideline and tested the plant's ability to comply with this particular response. So the plant's ability to provide reactive power control and voltage control was tested at two different power levels. The graph, XY graph shown on the left here, these are the measurements compared to a proposed California ISO reactive power requirement. So all blue data points there is actual measured reactive power of a plant at different active power levels. So you see that the plant, this data demonstrates that plant meets the expected reactive power capability, which is shown by this yellow triangle. In addition, the plant is capable of producing and absorbing reactive power at close to zero power production. We think this is pretty remarkable test because especially at the zero power levels, because this is somewhat is a replica of nighttime operation of a PV plant when there is no solar resource available, but it still can provide reliability services to the grid. So the plant was tested to demonstrate the control operation also in other modes, which I will go there in a second. But the 3D graph on the right basically is a more articulate view of the same test with also voltage on a 230 kilovolt line shown on a vertical axis to show that it's also being impacted during this test. So let's move on. This is a result of plant operation in a power factor control mode. So the plant was following the power factor set point signal and the power factor measured at the point of interconnection. And again, you see that the plant provides very good and accurate control, power factor control in this plus minus 0.95 power factor range in both cases. Move on. This is a voltage limit control test. No, I'm sorry. This is a reactive power control test that was also conducted as it's measured at the point of interconnection. So the plant was commanded to follow plus minus 100 MVAR reactive power set point, both inductive and capacitive. And in this case, about 100 MVAR per minute reactive power ramp rate was commanded to a plant controller. This is that low generation or close to zero power voltage control test I mentioned earlier. So again, this time series shows that at very low power levels, in this case, the plant was curtailed at only to 5 megawatt level. And by the way, this test was done, then there was a couple of hundreds of megawatts was available from a solar radiation. The reason we didn't do a nighttime control test just was based on the logistics of this experiment. So this is as close as you can get to a nighttime VAR control by the utility scale PV power plant. So we still have plans to demonstrate the true nighttime VAR support in the future joint projects. That basically takes us to the conclusions about this project. So the project showed how solar PV generating plants can provide a wide range of essential reliability services, has demonstrated fast and accurate PV plant response to AGC, frequency, voltage, power factor, and reactive power signals under a variety of solar conditions. To maintain the adequate level of reliability through the transition to high penetrations by variable generation, all resources need to provide sufficient voltage control, frequency support, and ramping capability. These are all essential components of reliable and bulk power system. One takeaway from this test, and I think it's really important for the whole industry, I think the accurate estimation of available peak power is really important for a precision AGC control, also provision of spinning and actually non-spinning reserves as well. Not so many plants have that capability, although the capability already exists commercially. There is no standardized way of evaluating it. There is many variables in a PV plant, such as resource, data itself, temperatures of the panels, characteristics of the inverters, and so forth, that needs to be taken into account. So we think this is an area where industry can join to get more standardized, if you will, process in what is in the best way of evaluating the available power from a PV plant when you're operating in a curtailed operation. Because conventional generation can do it very well, and we think there is still some room for improvement for PV. And by the way, to a certain degree, it's the same. It's also same area is true for wind power as well. So moving to our last slide, this is essentially conclusions to everything that all speakers just covered. So again, we demonstrated that PV generation can provide all essential reliability services as is described by NERC currently. It also can provide additional market services such as ramping capability, flexible capacity, and so forth. So we hope that data we produce will be useful to California ISO in their future market design, to other system operators in the US and worldwide. And we'll be happy to answer any questions by the audience, unless other speakers have something else to add. Thank you, everyone.
That's great, Juan. Thank you.
Thank you.
And do any of the other speakers have anything else to add? Just concluding remarks?
I think this is Mahesh. Just wanted to conclude with that correctly designed utility scale PV plants can do a great deal in terms of providing grid stability and reliability. This is, in that sense, I think it's different from, I would say, the extreme end of the rooftop PV, which generally would have a difficult time to provide the kinds of functionality that is expected from utility scale plants in general. Not that it cannot be done, but its perhaps is not as cost effective and so on. But from a grid stability perspective and reliability, the fact that these kinds of plants, which now the proportion of utility scale is growing in many markets, we believe that this is an incredibly important feature set required to ensure that with higher penetrations, that the grid continues to maintain the stability and reliability that's necessary for successful integration of large-scale solar generation. So
that's right. Thank you, Mahesh. And this is Vahan again. I just carried away with the technical stuff and forgot to acknowledge and thank all the staff in your organization that was very helpful at all stages of this project, also plant owner who was very helpful, all California staff for their contribution and organizing and taking lead in this project, and also U.S. Department of Energy, especially Dr. Gevorgian, who was supported all NREL activities. So thank you for the support of this project.
Okay, thank you. So that concludes our webinar for today, and I'd like to thank the panelists for the informative presentation. And now we have about 30 minutes to go ahead and get started with a Q&A session. If you have a question, please type your question into the GoToWebinar toolbar under the questions pane. We will get to as many questions as time allows. Just to start off, I've got one initial question that any of the speakers are welcome to answer. The first one is PV generation required to grid supportive services anywhere in the US or worldwide?
Who's going to take it over?
Would anyone like to jump in and answer that question?
Well, go ahead.
Go ahead, Juan.
No, I was just go ahead.
Clyde would be the right guy to answer that.
Could you repeat the question, Nika?
Absolutely. The question is PV generation required to grid supportive services anywhere in the US or worldwide?
So maybe, go ahead, Clyde.
No, I'm trying to see if I understand. Are they required to provide grid services anywhere in the US or worldwide?
Yes.
That's the question.
Okay. I'm not sure if they are required. I know in terms of there are a few things that the federal government has established in terms of requirements, right? So they need to be able to provide voltage and frequency ride-through capability. They also need to be able to provide reactive support, 0.95 lead, 0.95 lag at the generator step-up, or the high side of the generator step-up bank. But the other services that we tested this plant for, I don't think there are any requirements that I'm aware of that they have to be able to provide.
Yeah, so that's correct, Clyde. Juan, if you don't mind, can you go back to one chart that you had, or a couple of charts, back to the, because I'd like to use that to perhaps answer that question more fully.
Yeah,
Sure.
we're going back.
Back to the chart which talks about grid reliability and stability. That one, yes. Okay, one. So go that one, yeah. So if you look at the features that are required by NERC, in general, the voltage regulations, real power control, curtailment capability, frequency regulation, droop response, short circuit duty control, fault right-through. These are certainly features that we see in many of the utility scale PV plants, especially in US, but also more recently in other places as well, are increasingly either encouraged or already incorporated in the LGIA agreements. And particularly, we should be able to support like 0.95 power factor, leading and lagging, etc. So in that context, yes, those ones are there. Now, I think the broader question, which is if you, Juan, if you hit the slide one more time, the ancillary services, which is what was described here, I do not believe that those are capabilities that are essentially contemplated as being required. However, the effort in this particular webinar was to illustrate that these kinds of capabilities, now that they are available, can be leveraged especially in cases where PV plants are being curtailed for other reasons, to take advantage of them and in some ways reduce the constraint that only conventional generation plants can provide the services. I hope that answers that question.
Okay, thank you, Mahesh. One question, and this is kind of general housekeeping. Someone asked if the webinar will be available for download, and yes, it will. It will be on the ESIF website, and I will be following up with all of that information with the correct link. I have a question. Just a moment here. I have a question for Mahesh. Are the specifications of the inverter available publicly?
Yeah, so I think in general, the utility scale inverter manufacturers that we work with have all matured to a level where they are providing many of the capabilities that we leverage in utility scale plants, and particularly the ability to respond to signals to control P and Q power and reactive power, active power and reactive power in a fast manner. Most of the inverter manufacturers of utility scales are certainly able to do so, and so those specs are very generic in that sense. Now, when we started this exercise about 6-7 years back, we had to work with them to establish faster communications and ability for them to respond much faster than they had required in the past. In the fact that we have control loops of 100 milliseconds means that the inverter has to be able to receive that signal and respond to that. So that part of the specifications is being met by I think a small subset of the inverter manufacturers. But other than that, the specs are pretty generic.
Okay, thank you. And it looks like, Mahesh, you did answer some questions. So I'm going to read some that were not answered yet, and then we'll share your answers if we have time for some of the other questions. Another question I have is, what is the power ramp rate limit of the plant? And what is the power ramp rate requirement for CAISO?
Okay, so let me answer that. So, unlike conventional generation, the part that and this is Mahesh, utility scale plants can actually respond really fast. I mean, we can respond much faster than any conventional generation. So generally, the question that, or the challenge that we have is that how do we make the control system so that the plant responds at a rate that is what the grid operators would desire. So if they want a 10% per minute kind of a rate, then we can slow down the response of the plant to be able to do this. Now, all of these answers are within the respect of the resource being available. In other words, if the resource dies suddenly, then there's nothing much we can do about that. But as long as, for example, the resource is available, that's a solar resource, then we can certainly ramp up the plant either very fast, much faster than any conventional generation, or we can slow it down to ensure that the grid does not see a huge impact. So I think the question is hard to answer, because I would say you can do it at infinite rate, but that's not very meaningful, I presume.
Okay, thank you. Another question I have you used droop control for voltage regulation as well?
The answer is yes.
Okay.
Not in this particular, but that was been demonstrated in a previous years.
Okay.
Yeah. So the utility scale plants can be controlled to have voltage droop. Yes.
Okay. Another question I have is, how can you justify the PV curtailment with the AEP loss when providing AGC?
That's a good question. So the question is, Hey, this is great. You can do AGC, but then you are leaving you are basically losing certain amount of energy due to curtailment. So I think that is a trade-off that the plant owners can perhaps make. The other answer is that if the plant is already being curtailed for a variety of other reasons, which Clyde already explained, then you're already being curtailed. Why wouldn't you want to use that plant to provide other services while it is being curtailed? So, but it's a very good question. There is the downside of leaving certain available power not being utilized at any particular time. I hope that explains it.
Okay, thank you. Another question I have is, do the inverters have any special feature to be able to do these controls?
As I explained, I think in general, most utility scale inverters are capable of providing PQ controls. They generally operate at a much faster rate. The switching frequencies is of the order of several kilohertz, and so as long as the inverter manufacturer ensures that those capabilities are available externally from a controller, then yes, it is available.
Okay. Have the inverters have you tested the system in islanded mode?
No, because this is a utility scale PV plant, and in order to operate in islanded mode, you have to have grid forming inverters and local load. So it wasn't the purpose of this plan. It's a commercial utility scale plant, so it's not physically possible to do it. But there are other projects at the smaller scale that look at the PV as a energy supplier in a microgrid, where this is done in many places in the world in the U.S. But that's a kind of a subject of different area of work.
Okay, thank you. Another question I have, which markets demonstrate the best approaches to making best use of the capabilities described here?
That's a difficult question, right? So right now we think the regulation market might be someplace to participate. We also think that, as Mahesh said, if the plant's already being curtailed, you could participate, and if you know most likely you're going to be curtailed, let's say during certain hours, then you could participate in spinning reserve or non-spinning reserve markets, and even frequency response you could participate in.
Okay, thank you. Next question, to provide frequency support services, do you have any idea how much money is lost for curtailment and how much is gained from the ancillary service market?
No, we didn't do any type of economic evaluation.
Okay.
The other thing too, Nika, on our website, we have prices posted for ancillary services, and I think a developer could go in, look at the OASIS site, look at the prices, and see if it makes sense to, or what market makes sense to participate in.
Okay, thank you. Another question, can the power electronics and inverters be used for grid support at night? Or
go ahead, I'll finish the question.
Or must there be power from the PV available to make those assets useful?
Yeah, so this is Mahesh. Let me answer that question. So first of all, power electronics and inverters and the controller, you need all of those functions, can indeed be used for providing reactive power support at nighttime or voltage control support at nighttime. It doesn't need any PV power for that, and the reason is that the reactive power is between the grid and the inverter, the AC side of the inverter, and the inverter can basically absorb power, very little, turn it around and change its phase angle and send it back to the grid, minus whatever losses because of the losses in the inverter, etc. So yes, they can indeed provide grid support at nighttime. I hope that answers that question. So yes, this would be a useful way of using that asset if a grid operator or the asset owner has need for supporting voltage or providing reactive power during the time when the PV plant is not producing any active power.
Mm-hmm. And to just build on that, Mahesh, one of the tests we did was, remember, we took that plant all the way down to 5 megawatts. And at 5 megawatts, it was able to provide full reactive, which was, it was able to take in 100 megawatts of reactive power and also produce 100 megawatts reactive. So in other words, at night, that plant could take a small amount of megawatt from the grid and turn around and convert it and provide full reactive capability as though it's operating at full capability.
Mm-hmm. Right.
Okay, thank you. Next question I have is, how well designed are California's current utility PV grid connect systems at providing these reliability services?
Clyde, go ahead.
Well, I think the grid's pretty well designed. We just need to look at places we have challenges. For instance, like where we have high voltages. See if we have PV plants there that can help us, like at night. So the first phase of this test was to really look at the plant's capability. The second phase now is to go back and evaluate the existing solar fleet that we got to see which ones have the capability to provide these services that we tested. And then later on this year, we're going to have an actual PV plant participate in regulation service, as a test. So gradually, we're going to open up the markets and other services for these asynchronous resources.
Yeah. So one of the so let's talk about AGC, for example. So what is necessary for that is the ability to receive, and I'm just talking about technical aspect, not commercial aspect, but ability to receive an AGC signal from the KLISO system. So most of the utility scale plants that we build have a KLISO rig, for example. That rig is utilized to actually send data to KLISO from the plant itself, and it can receive the data in the other direction as well, which could be an AGC signal. And then the second aspect is then tying that AGC signal with the controller. And so these are all capabilities that we're going to test out, and it's not rocket science to make that happen.
Okay, thank you.
Okay.
Another question I have is, does this 300 megawatt test plan have battery storage installed?
No.
Oh.
Okay.
In fact, the purpose of this test is to demonstrate the ability of PV technology itself. So yeah, if that plant had storage installed, we probably would never do a test there, because this is a PV demonstration only.
Okay. Okay, considering the interaction of the inverters within the plant, what is the approximate time response of a 300 megawatt PV plant to an active step command from ISO?
So it's a question of if the question is about, let's say, reactive power, it can be changed in a couple of seconds. If the question is about active power, that also is pretty fast, I would say. So we have some data that the questioner wants to, we can send a white paper on that subject that was published a while back.
Okay, thank you. What was the maximum power rating for the inverter that has been used?
So the inverters, the 4 MVA, yeah. Mm-hmm.
Okay.
But maybe the question was more like, that's why we're calling it a 4 MVA, because it's essentially if we put 0 active power, it would be 4 megawatt in general. If we have some reactive power, we can produce up to essentially theoretically 4 MVARs as well. Yeah.
Okay, thank you.
Perhaps the questioner had some other thoughts.
Okay. I have a question about cybersecurity. It looks like smart inverter is a critical part of these features to be utilized. Do you have any updates regarding smart inverter deployment? Any concerns about using smart inverters such as cybersecurity?
So I think the way I would say it, this is, first of all, we're talking about utility scale plants, not talking about inverters themselves. And remember, I keep saying it's a plant, it's not the inverter. Inverter, it's just one element of the overall plant. So the plant itself, we do have systems where there is an electronic fence around that, so that there is, and this is required by the NERC compliance as well, especially for large plants. And so that cybersecurity is maintained in that context. Now, but perhaps a bigger question that might be what the questioner might be asking about is that if we start going to a smaller size and smaller smart inverters, distributed PV and all that, how does it all work out on from a cybersecurity perspective? And I do not know. It's a challenge.
Okay. Okay. I have another question for First Solar. How does First Solar estimate the power available from the sun at any given time?
This is a good question, and this is what Vahan was saying, that it needs a little bit of thought. Now, I'll give a general answer, and the general answer is that we do know from the inverters themselves as to what power they can produce. They do MPPT tracking, which is the maximum power point tracking. And so when we curtail them, we kind of have a good idea of where and how much we're curtailing, so we can use that information. There are other ways as well, but we are currently working through those means to figure out what is the most accurate way. And remember, I'm talking only about the pretty much instantaneous available power. I'm not referring to what the power would be 5 minutes from now, an hour from now, right?
Yeah.
Okay, thank you. Next question, is there a constraint on the number of inverters within a plant due to communication delays? What kind of communication is used between controller and inverters?
Another good question. In general, we have not found that to be the limiting factor. The fiber communications is pretty fast, and even the 100 millisecond loops are fast. Actually, the communication piece is the least of that concern. It can communicate much faster. So No limit found yet.
Okay.
The question was about also protocol, Mahesh. Is it Modbus? Is there a particular protocol that you can point out?
We generally we have used quite a few different ones, but all of them are generally based on TCP/IP protocols, and I think the Sun specs have got some standardization. But before that standardization, when we started, we used a specific protocol that Ether IP protocol that was pretty fast, and that's been used in industrial applications by companies like Rockwell, and that we found to be quite adequate.
Okay. I have a question about older plants. Do older plants need new inverters to do this kind of control?
That's a very good question. I think I would say it is a function of what kind of inverters there are. As I said, there are inverters and then there are other inverters. So depending upon the feature sets available with the inverter, it will drive that decision. But generally, I would say most modern inverters should be capable.
Okay. Next question I have, are you using PMUs to synchronize the two feeders connected to 230 kilovolt system? Is there any line between them?
No, we are not using PMU to synchronize them, no. The PMUs are just utilized, in this case, we were just referring to them as a way of collecting the data, and that's all. PMUs are not used in any control fashion.
Okay, thank you. Another question, is there a study to understand impact to the modules themselves due to the curtailments?
It's a good question. We do worry about that, and we have worry about that in the sense that we understand the implication of that, which is that the modules are, for example, if the inverters are completely turned off, then essentially the modules are not producing any power and would have higher temperature in general. So, but all of those aspects we have tested as a module manufacturer, and in general, we do not see issues associated with that. Just remember, I mean, the modules are exposed to high temperature all the time, right? Because after all, if they are collecting 20% of the sunlight, or they are collecting a fraction of the sunlight and converting it to electricity, everything else is just hitting the modules and turning into heat or whatever else it's supposed to do. So.
Okay, thank you. So I have one question about a specific slide that I can navigate to in just a moment. This person wants to know, please describe how regulation accuracy is determined. What accuracy determined for provision of fast ramping or other services, or how would that be determined? And this is slide 26, so let me get back there.
Is the slide there to answer? Or I can?
Yeah. Yeah, we do have some documentation on our website as to how we do this calculation. But essentially, you know, we issue that 4-second dispatch instruction, and then we go back and look and see how well that unit was able to follow that instruction. And then, so we accumulate that across, I think it's a 15-minute time frame, and then across an hourly time frame, and look at the accuracy of following that, the dispatch signal. So, so I think, yeah, there's a document out on the ISO's website that goes into how we do this accuracy calculation.
Okay, thank you. Okay, we've got time for maybe just a couple more here. While active reactive powers are independently controllable at an inverter level, is it correct that active and reactive control is also at the plant level? Hang on just a second. I'm not sure if exactly if this is a question.
Yeah, so I think I can answer that.
Okay, thank you.
There is first of all, the endpoint is the overall plant control. So that means we are controlling the output of active and reactive power at the point of interconnection. So once that objective is clear, then we are basically controlling each of the inverters so that both active and reactive power together, when aggregated over the whole plant minus whatever losses and everything that works out, is what is the desired value. So yes, they are being controlled separately, and it is being controlled at the plant level and at the inverter levels as well individually.
Okay, thank you. And I probably have just one more question. If a PV plant is providing controlled curtailment, doesn't that need to be included in the PPA provisions, and do you see a trend in this happening?
Well,
so go ahead, Clyde.
No, we do have in the PPA some curtailment provisions, right? But there are times, you know, if you have, let's say, oversupply, you will have to curtail. There are times when if you have congestion on the system or you have any real-time problems, you're going to have to curtail resources. And it may be any type of resource, including PV plants. So not necessarily, you know, during the curtailment provisions that we have.
Okay. Okay, well, thank you. We are at 12:31 now, so that's all the time that we have today for the Q&A session. Thanks again to our speakers, and just want to let everyone know that we will be posting today's presentation on NREL's Energy Systems Integration website on the past seminars and workshops page. And you can find that at nrel.gov/esif/seminars-workshops.html. And I will also be posting the PDF version of the presentation there. We will also be posting some of the questions that we couldn't get to, and we will provide answers to those questions on that same page. And if you guys have additional questions that you weren't able to ask, you can send those to esi@nrel.gov, and we'll get back to you on those. That concludes today's webinar. Thanks for attending.
Thank you, everyone.